Before watching this lecture, you should have an idea of how to do confidence intervals in the linear regression model when we have only one explanatory variable, and you should be aware of hypothesis testing in the LRM with several explanatory variables, because that's what we'll do here. We'll look at how to create confidence intervals in the linear regression model when we have several explanatory variables. So the setup is standard when we want to do inference. We have the LRM, random sampling, Gauss-Markov assumptions. The error term follows a normal distribution. Conditionally on x, we need that for the inference to be exactly correct. But as we have discussed, if it's not normal, it will be pretty okay as long as n is not too small. So let's look at this example again. 99 students, the result on the final exam, SAT score verbal section, SAT score math section, and the high school GPA. And since we have the Gauss-Markov assumptions, OLS is best linear unbiased estimator, and here are the OLS estimates. So what we want to do now is create confidence intervals for the beta parameters. This number here, 0.02866 and so on, is called a point estimate. It's our best estimate of beta 2, but by itself it's kind of useless because it just does not provide any kind of information about the certainty. Like, is it 0.029 plus minus 1, in which case it would be terrible, or is it 0.029 plus minus 0.001, in which case it would be awesome? That's the kind of questions that we can answer by finding the confidence interval. So confidence intervals, first thing we have to do is to decide the level of significance. So if I decide on an alpha which is 5%, then I would create a 95% confidence interval. So for an arbitrary alpha between 0 and 1, the confidence interval would be a 1 minus alpha times 100%. And we create those for all the betas. So I can do it for beta 1 through beta k. The formula for the confidence intervals is extremely similar to the formula that we discussed in the case when we had one explanatory variable. So at the center of the confidence interval is the point estimate b. To this point estimate, we do a plus minus a critical value multiplied by a standard error. The only difference is that for the critical value, it's alpha half comma n minus k in the general case. When we first discussed the confidence interval, we had just one explanatory variable, so k was 2, and that's why we wrote this as plus minus t alpha half comma n minus 2. But to generalize this, we have to write n minus k. So based on a printout like this, it's very easy to get the confidence intervals for each of the betas. For example, if I want the 95% confidence interval for SATV, I do this point estimate plus minus the critical value, which I can find here, statistic tables, T. The degrees of freedom is n minus k. You can see here that n is 99, k is the number of rows here, so n minus 99 minus 4 is 95. If I want to do 5%, then I should put 0.025. So the critical value is this one. confidence interval for SATV, this number plus minus this number times the standard error. If you find it boring to calculate these yourselves, you can ask Gretel to do it. Just go to analysis, confidence intervals, and you have them right here. So for SATV, that's the coefficient, that's the point estimate, that will be the center of the confidence interval, left-hand limit, right-hand limit, and it will give you the 95% confidence interval. If you want to change that and do, say, the 99% confidence interval, you can do this, and it will then obviously be wider. In eViews, you will go View, Coefficient Diagnostics, Confidence Intervals. And it typically gives you 3. If you just want the 95%, we can just do this, and that's the confidence interval. Point estimate, left-hand limit, right-hand limit. And the interpretation is as before. There is a 95% probability that the true beta 2 is in between these two numbers.